Okay. Good evening. His Excellency, Mr. Scott Wyman, British High Commissioner, Dr. Eugene Tan, Gallery Director, Ms. Chong Siak Cheng, CEO of the National Gallery, Professor Brian Cox, Mr. Robin Ince, distinguished guests, ladies and gentlemen. Welcome to this very special edition of the British Council Knowledge is Great lecture. My name is Shabir Aslam. I'm the Director for Education at the British Council here in Singapore. Absolutely delighted to welcome you all to this wonderful venue. I'm sure you're all as excited as me to welcome Professor Brian Cox to the stage, so we're going to try and keep these introductions very short. So without further ado, first up, please let me introduce my good friend and President of the University of Manchester Singapore Alumni Association, Mr. Hian Seng Tan.
His Excellency, Mr. Scott Wyman, British High Commissioner, Professor Brian Cox, distinguished guests, fellow alumni, ladies and gentlemen, good evening. Welcome to another session of our exclusive In Conversation series and to this very unique edition of the British Council Knowledge is Great lecture, the In Conversation with Professor Brian Cox. This follows from our last In Conversation with University of Manchester President and Vice Chancellor, Professor Dame Nancy Rothwell, and 2010 Nobel laureate, Professor Sir Andre Gam in April. This evening, we'll hear from our university's esteemed Professor of Physics, Professor Brian Cox, and Mr. Robin Ince, Brian's partner in his BBC show, The Infinite Monkey Cage. We're delighted that the British Council, together with the university and the Alumni Office, have worked together in bringing this event to the National Gallery. On behalf of the university and the Alumni Office back in Manchester, I would just like to highlight a few important points to fellow alumni and guests. Manchester has had an outstanding academic year for 2015 and 2016. This year, Manchester has been named European City of Science for 2016 and hosted the European Science Open Forum, which concluded last month in July, which university played a major part in, as well as Professor Brian Cox. Manchester's research in science and engineering is growing from strength to strength, from opening of the National Graphene Institute to breaking ground on the new Manchester Engineering Campus Development Project, or MECD. MECD is one of the single largest construction projects undertaken by any higher education institution in the UK. This £350 million project will see Manchester investing in world-class research, teaching, and learning. And MECD will be a destination where engineering will be on display and revolutionary science will be visible to all. On top of that, there's a £50 million investment in our Alliance Manchester Business School. So for those alumni who hasn't traveled back to Manchester for a long time, please make a plan in your calendar and find a chance to travel back to Manchester. You'll find a dramatically changed campus with a £1 billion investment in new buildings and facilities, supporting students and research. This includes the completion of the award-winning refurbishment of the Whitworth Art Gallery and the new state-of-the-art Manchester Cancer Research Centre. So the Alumni Association will continue to work closely with our university to bring more distinguished professors like Professor Brian Cox and senior management team to Singapore to engage fellow alumni. The Alumni Association is also launching our annual membership that with the committee members work together with merchant partners in Singapore to offer attractive discount privileges to paying members. So the committee is looking forward to your full support to sign up for the annual membership and also your active participation with the activities we organize. On this note, I would just like to introduce our friend and partner for tonight's event, Mr. Roland Davis, Director for British Council Singapore. Roland, please. Thank you.
I think my job is to be extremely brief and just say a very quick couple of thank yous. Obviously, the main attractions here in front of me. But I would like to say thank you very much to the University of Manchester for lending us your esteemed scholar. And also thank you very much to the National Gallery. It's a real pleasure to be in such a wonderful setting as this. And we are very much looking forward to working with the National Gallery in future. But please have a wonderful evening and enjoy this evening with us. Thank you.
can we now welcome His Excellency Mr. Scott Wyman, British High Commissioner.
Thank you, Shabir. Ladies and gentlemen, it's a great pleasure for me to be here this evening as well. And I want to add my thanks to Roland, to the National Gallery for providing such a terrific venue. It's great to hear the update on all the developments that are going on in Manchester with the university at the moment. Obviously a city that's driving forward development in the north of England. The one thing that your president didn't tell you is the thing that stays the same in Manchester. It's not, I'm not going to say it's the weather, it's Curry Mile is still there, okay? So any of you that go back there, you can still get a fantastic curry somewhere along that fantastic golden stretch of Manchester's streets. But it's obviously the main reason that you're here this evening is to hear Robin Ince and Brian Cox, Professor Brian Cox, in conversation. Robin, in partnership with Brian in recent years, has done a tremendous amount to bring science to a much wider audience. And they have employed really imaginative, creative ways of doing that. And Robin in particular, he's not a scientist himself, but he's somebody who's just interested, and through that interest and through the way in which he can ask the right sorts of questions, he helps people understand that science is not something that's beyond our reach, those of us who haven't necessarily studied it professionally. It's something that we can engage in and that can enrich our lives. And that's what's going to happen this evening, I think. I'm sure that through their conversation and through your opportunity to have questions and answers through them, we will leave the hall this evening enlightened, but also enriched. And so I'm sure that you're going to have a very rewarding evening. Thanks again, everybody, for coming, and enjoy yourselves.
Ladies and gentlemen, can we now welcome Professor Brian Cox and Mr. Robin Ince to the stage.
Hello. This is, by the way, Curry Mile is right next to the Whitworth Gallery as well. So you can just enjoy the art, then have a curry, and it's very near the Science Museum as well. So you can have the three cultures, not merely the two cultures. We'll start off by, well, I've just been reading your new book, in which, with Jeff Forshaw, also based at Manchester, you show, well, how we know what we know in terms of the weight of the universe, the size of the universe, the possibility of multiverses, bubble universes. And I thought, why did you go from academic science to the majority of your work? As we know from, we did a show in Manchester where the main question from the audience was, will you ever come back to Manchester University to lecture us? And fair enough, 2 years later he did. What a lot of posts you had. But why communicate science? What for you is the important idea of taking it from research and giving it to people who may have imagined they had no interest in ideas of why our universe is as it is?
Yeah, before I start, I just want to add my thanks to the National Gallery here and to the British Council and also to the Manchester Alumni Association for organising this event, so thank you. It's an interesting question. The first thing to say is that I came into public engagement, communicating science, by accident in many ways. I was working, I'm sure we'll talk about it, at the Large Hadron Collider at CERN in Geneva, which Manchester, along with many universities across the world, played a big part in building the detectors there. And I was being a postdoc, doing my research there. And the BBC appeared because they were interested in the building of this giant machine. And interviewed me and sort of liked the way that I spoke, and then interviewed me again, and then said, would you like to make a small BBC4 programme? BBC4 is a smaller channel the BBC have on the Large Hadron Collider, and it sort of snowballed from there. And I'm often reminded of the idea that you should never be a politician and run a country if that's what you want to do. And it's the same, I think, with public understanding or engagement in a way. It's not something that many people choose to do, in my experience. You tend to be a researcher and you fall into it accidentally. But I think the best answer to the value of public engagement is perhaps not to teach people or to tell people about the discoveries themselves. You know, the age of the universe, 13.8 billion years, 350 billion galaxies in the observable universe. What do you need to know? They're all interesting things. It's entertaining. But ultimately, there's a very famous essay which was based on a speech by the Nobel laureate Richard Feynman, an iconic theoretical physicist. I think it was back in 1953 or 1954. And he gave a speech to the American Academy of Sciences called The Value of Science. And so he talked about the fact, of course, that our modern civilization is built on science and engineering. The great discoveries obviously feed through into everything that we take for granted today, increased life expectancy, whatever it is. But he said, actually, the most valuable thing is what he called the philosophy of science itself, and he called it a satisfactory philosophy of ignorance, which I think is a beautiful kind of term. It is merely satisfactory. It's no better than that. And it's a philosophy of being ignorant. And what he meant was that, of course, the way that science proceeds is you come up with a theory, you look at the world, you try to explain it. You're more often than not, almost always, as certainly a theoretical physicist, you're almost always wrong. You are certainly never absolutely right. You can be temporarily right and approximately right for a while, and then some new data comes along and your theory must be refined or indeed jettisoned. And his point was that it's a very humble approach, and it's not often communicated as that, actually. Quite often it seems that scientists are priests who sit on top of a mountain and pronounce on the way that the world works and what people should think. Nothing could be further from the truth. That idea that science is a satisfactory philosophy of ignorance, I think is central to the success science has had at explaining the natural world as we see it. But it's also, Feynman points out, a useful approach to all human endeavour. The fact that being an absolutist is someone who really is. There isn't great value in being an absolute, in believing yourself to be absolutely right. What we might call a Trumpian approach, I suppose, these days. That's not only is that not the way to discover how nature works, but it's not really the way to run humanity. So I think that's a very interesting perspective that Feynman had on the value of science. And so I suppose most of this talk, we'll talk about what we know about the universe, what we know about particle physics, Higgs particles, etc. But underlying it all is that philosophy of ignorance, which is a valuable thing.
Well, that's just as a follow-up to that. Why do you think it is that we've heard this term now, a post-fact world? We are in a civilization where, from things like the combating the early mortality of children, the access to warmth, to security, to vaccination, so many things. And yet, on the other side, as you were mentioning there with the Trumpian values, we also have a rise of a new dogma, which doesn't seem to be needed in any way to be bedded in evidence-based thought. How can you, in the communication that you practice, how can that effectively combat those issues?
I think it's when I should say that we're here. We're on our way through. I always stay in Singapore for a few days at least because I enjoy the country a lot. But we're on our way to Australia, where we're going to do some live shows, and at face value, those shows, and we'll talk about it, are about cosmology, about what we understand about the origin and evolution of the universe. Actually, in fact, before the Big Bang, which is a semantic point in a sense, but we'll certainly talk about that as well. But underlying that, the things we talk about now in modern cosmology are almost ridiculous. We talk about a universe with 350,000 million galaxies like the Milky Way. How do we know? How did we count them? We talk about a universe that's 13.8 billion years old. How do we know? How did we make that measurement? So all those facts, the precision with which we can describe the evolution of the universe from, let's say, less than a billionth of a second after the Big Bang, and actually even speculate about what happened before that, is quite remarkable. But the parallel is, of course, this kind of undercurrent is how did we know those things? How do we know? How can we speak with confidence of a measurement of the age of the universe, or indeed the age of the Earth, or the mass of the Earth, or the mass of the Sun? How were these things done? They took deploying that philosophy of ignorance. Really, they're the fruits of that. So I think what you can see when you look at the precision of our understanding of worlds beyond our experience and conditions so far away from human experience, it's almost impossible to see how you could get a handle on it. That same process, I think, and Feynman thought, and many think, can be deployed for questions, not only questions with direct connection to science, like climate change and how perhaps we should respond to it, and what's the most likely outcome if we carry on, all those things, public health policy. There are obvious areas. But I think that also that as I said, that deploying that philosophy of ignorance can be. It can be. I'd like to say it could be deployed throughout human thought, with caveats. Of course, you don't develop policy necessarily. It's not a logical. You can't just press a button and develop policy. There's obviously opinion in that, but you can measure the effectiveness of policy based on some frame. Anyway, we should talk about some science.
Well, I suppose one of the things we talk about a lot in our show is trying to remind people that science is not about coming up with the right answer; it's coming up with the least wrong answer, and the hope that you get. And that's a very enjoyable and a fascinating journey.
You see it with modern cosmology is based on Einstein's theory of general relativity, which is a theory of gravity. So in that sense, the ambition of the theory was no greater, really, than Newton's. It was to describe how objects move in gravitational fields. Newton said it's an apocryphal story actually, but Newton said there's an apple fell onto his head. Why did it fall onto his head? Because there's a force pulling it down, and that force is proportional to the product of the mass of the Earth and the mass of the apple, and the square of the distance between them. So that was the first universal law of nature, 1687. So a great step forward. In 1915, based on thoughts that Einstein had for actually a decade or more, Einstein produces a new theory of gravity, which the one-line summary is that the apple doesn't hit Newton on the head because the Earth pulls the apple down. The apple hits Newton on the head because Newton accelerates upwards and headbutts the apple, which was floating there, minding its own business, having become detached from the tree. So it's completely the opposite picture. It's a very counterintuitive picture. Einstein's basic, the genius of Einstein was to realize what we all see now. If you look at the International Space Station and the astronauts floating in it, we're quite familiar with the fact that although those astronauts can be described as being in free fall, freely falling towards the Earth, it looks for all the world as if no forces are acting on the astronauts at all. So if an astronaut gets a cup of water and lets go of it, then it just stays there. It gets a feather and puts it there, and it stays there. It gets a big 1 kilogram mass and puts it there, and it stays there. So the thing that Einstein noticed, which is not explained in any way satisfactorily in Newton's theory, is that obvious thing well, it's not that obvious, but it's obvious if you look at astronauts, that all things fall at the same rate in a gravitational field. If you remove air resistance, so you drop a feather and a hammer, it was famously done on Apollo 15 actually on the moon, drop a feather and a hammer here. If air resistance is taken away, if there was a vacuum here, they would fall at the same rate. It's an unusual, that's central to the behaviour of gravity. Newton doesn't explain it really. Newton's theory works, but it's rather convoluted. There's no real explanation of that. But in Einstein's theory, the explanation is that they're not falling. It is the ground that is accelerating up. And these things are just sat there minding their own business. Complete redefinition of the picture. But that led... So that's the ambition, Einstein's ambition. He was interested in that. How do I explain that? That led to essentially a geometric theory of gravity, which is that there isn't really a force of gravity at all. What there is the curvature of space and time, because he'd already merged those together in 1905. So the bending or curvature of space and time by mass. So you picture why does the Earth orbit the sun, according to Einstein? Because the sun curves space and time in such a way that the straight line, the path of falling, essentially, around the sun is actually an orbit. And you might say, well, how is it? How could you replace a force with geometry? And actually, there's a beautiful analogy that you can see that. If you imagine the surface of the Earth, and you imagine standing with your friend at the equator, and you agree to walk due north, so you set off. Now, the parallel lines on the surface of the Earth are lines of longitude. So what you find is you get closer to your friend as you head to the North Pole, and in fact, if you got to the North Pole, you bump into them. So if you didn't know that you were moving on a curved surface, you would conclude there was a force of attraction between you, pulling you together, because you were minding your own business, trying to walk parallel to your friend, but you kept getting closer. You get closer because you're on a curved surface. And that's exactly the way that Einstein's theory works. So that's kind of interesting. And that provides the kind of explanation in rough terms for why things fall at the same rate in a gravitational field. It's just that they're minding their own business, following the same straight lines through the same curved space. So you think, okay, beautiful. It makes some predictions that were better than Newton's. It predicts the orbit of Mercury more accurately, for example. But then Einstein noted, it's a very long answer to a simple question, I know. Then Einstein noted, and with others actually, that something that was he described himself as the most audacious leap he'd ever taken. He actually wrote to a friend and said, this suggestion may confine me to a madhouse, or see me confined to a madhouse. So audacious is it. But he realized that you have a theory that it tells you, if you put a sun there, a big blob of mass, it tells you what happens to space and time, how it curves. So in a sense tells you the story or the history and future of a solar system. And that worked very well. So Einstein said, okay, well, therefore, could I not apply this to a universe? If I knew the matter distribution of the entire universe, would my theory tell me the history, the past, present, and future of the universe in the same way that it allows me to predict the orbit of planets, so the position of a planet at some point in the future? And it turns out that you might say, well, I can't do that. How can I decide to know what the distribution of matter in the universe is? So what Einstein and a Belgian priest, actually, called Georges Lemaitre, and some others did, was say, well, we'll make the simplest assumption, which is that it's uniformly distributed on large scales. So in that direction and that direction, everywhere you look, it's roughly speaking the same. What does the theory tell me? And the theory tells you that the universe is either expanding or contracting. In other words, it tells you that there was an origin, because if you've got an expanding universe today, it means it was smaller in the past. So the theory actually predicted the Big Bang, the origin of the universe. And Lemaitre, the priest, he was a very eloquent man, and he wrote to Einstein and said, your theory predicts there was a day without a yesterday. And Einstein wrote back to him, this goes back to being humble. He wasn't very humble on that day. And he said, your mathematics is excellent, but your physics is lousy. Because Einstein was very uncomfortable initially with the idea that there was a beginning. He much preferred, initially, an eternal universe. But it turned out he was wrong. His theory is unstable in that respect. It predicts that the universe had an origin, essentially. And it's a remarkable story, and the reason I kind of went on that circuitous thing, because it tells you that that Einstein didn't begin with some grand vision of predicting or trying to work out with a pen and paper that the universe had an origin. He wasn't interested in cosmology, really. He was interested in the behavior. He wanted to know why things fall at the same rate in a gravitational field. And it's one of the most remarkable feats of the human intellect, but also a quite remarkable demonstration of the power of science, that thinking about that behavior leads you to a framework to speak of the origin of the universe itself, predicted it. About 2 years later, Edwin Hubble showed that you look at galaxies, distant galaxies, and they're all receding from us. And the more distant they are, the faster they appear to be receding. And that's the signature of an expanding universe. That was 2 or 3 years after the prediction from Einstein's theory. So there's the power of science and the power of abstract thought.
But that's that lovely thing as well about when we were talking about science being the least wrong answers. There are people we've argued with who've said things like, if science is so good, why do they keep having to change it? And you go, that's kind of why it is. And then also when someone goes, oh, but Newton was wrong. And you go, well, Newton was kind of wrong, but he was right enough for his equations being used to get us to the moon. So in terms of wrong, it's pretty good wrong, isn't it?
It's, it was good wrong.
So because we're on Einstein, we should talk, I suppose, about one of the major science stories of this year, which is such a remarkable story, which is, physics does require sometimes delayed gratification. People can come up with an idea and go, but unfortunately the technology is not yet here. Now, gravitational waves, we have the detection of gravitational waves from history which involves two black holes merging and very briefly a power output 50 times greater than all the stars of the universe, which is a great first scene for any physics movie. So can you give us a little bit of the background of how, in the last year, we have detected gravitational waves and yet again proved that Einstein's ideas were very strong ideas?
Yeah, this is many of you will have read about this. It's an experiment called LIGO. And essentially what LIGO is a set of rulers. They're laser rulers, and they're about 4 kilometers long. And there are two sites, one in Seattle, near Seattle in Washington State in the United States, and the other one in Louisiana. So at each end of the United States, so separated by, 2,000 miles, I suppose. And the rulers are at right angles to each other, and they're laser beams. So you're essentially measuring the changes in the distance between mirrors at right angles to each other with a 4 kilometer long laser beam. So very high precision measurements of changes in distances. And what Einstein's theory predicted, and Einstein was well aware of this, was that I said that mass, the basis of the theory is that mass curves space and time. So that means that if you've got masses that move and things that happen, violent things that happen, you can get ripples in space and time that move out, just like ripples on a pond if you throw a stone into the pond. So these ripples in space and time from violent events will be passing through this room now because there have been very violent events out there in the universe. But they're very, very tiny shifts. I can't quite remember the number, but it's something like a 100,000th of the diameter of an atomic nucleus or so. Very, very tiny shifts in these 4 kilometer long rulers. But you can measure it using a process called interference. So you can measure very tiny changes in the distances. So what the measurement was that we realized that 1.3 billion years ago, so 1.3 billion light years away, 2 black holes collided. And those black holes were of order 30 times the mass of the sun each. They collided together. As Robin said, they outshone the power output of the entire universe for a fraction of a second in that collision. So a huge amount of energy. But the way actually you can see how much energy there was, there's a graph in the paper that LIGO released that shows these black holes. So they're orbiting around each other, radiating energy away through the gravitational wave, shaking up space and time as they go, and spiraling in. And there's a plot where you see the closing velocity of the black hole. And it's measured in tenths of a second. And you see that, so in 1/10 of a second, the closing velocity goes from 1/3 the speed of light to 2/3 the speed of light. So you imagine accelerating something 30 times the mass of the sun towards the other thing with a change in velocity that's 1/3 the speed of light in 1/10 of a second. You realize that there's a lot of energy in that system. Incredible. And then they merge together. And you get, obviously, a bang and space-time shakes. And LIGO saw this signature 1.3 billion years later, which passed at the speed of light through the one, I think it went through the Seattle one first and then through the Louisiana one with the right delay. So you see the signaling one, and then light travel time across the United States, signaling the other one. And it's the signature. And so you can work out what happened. What's tremendous about, I mean, it's also, first of all, it's incredible for so many firsts. It's the first time we've seen black holes that large, actually, huge, 30 times the mass of the sun. It's the first time I mean, we know that they're in the centre of galaxies, but this is a direct observation of them. Secondly, it's the first time we've seen them collide together. Thirdly, it's the detection of gravitational waves, which is a prediction of Einstein's theory 100 years ago. But fourthly, it opens up a new window on the universe, because if you think about the history of astronomy, going back, well, as far as human history, really, but with the telescope, Galileo and all we've done is look at light. And light is, you can make very detailed measurements of the cosmos, but much of the things that happen, many of them are obscured. There's a lot of dust in the universe. You can't see back beyond 380,000 years after the Big Bang, because before that time the universe was opaque. Maybe we'll talk about that a little bit later. So you can't see back with light beyond 380,000 years after the Big Bang to the earliest times. But with gravitational waves, they go through everything. They don't care about dust. They don't care about the fact the universe was opaque until quite some time after the Big Bang. They just travel. So in principle, you can view, even in principle, you can view the Big Bang. You can view. You need a more sensitive set of detectors, but now we know it works. You can imagine at some point in the future, essentially using gravitational waves to probe the origin of the universe itself. So it's a remarkable discovery. But again, probably the most remarkable thing of all is that it was predicted by Einstein with a pencil, essentially, using his brain back in I think it was about 1918 or so, I can't remember, 1919. Not long after the theory was published, they noticed that gravitational waves were a prediction.
Well, that's something as well, just for a general audience, to give them the tools sometimes to do their own experiments, because that's one of the things that I particularly enjoy, which is you often imagine you require making your own particle accelerator, which takes a lot of time. But there are other things.
Well, everyone had one, of course, an old television set. You know, before, when you had an old tube television set, you had a particle accelerator. Because no one has them anymore.
Oh, I feel like an idiot. I threw mine away. But it's so, for instance, measuring distance. Now, this is something we were talking about the other day, where when we were talking about, for instance, the distance of Neptune and the tools that may well be required for doing that. And I wonder if you can just guide people through how they would be able to, if they particularly want to pick certain planetary objects in our solar system, how they can measure them.
Yeah, I mean, actually, just on our way here, we were talking about astronomy and saying it's quite difficult from the centre of Singapore, because obviously you have a light pollution problem here, but you go out into the anywhere. So actually, south of Manchester. So we're talking about Manchester. The book I've just finished with my colleague at Manchester, Jeff Forshaw, starts. We get to talk about all these exotic things that happen in the universe, but we start with going back to the beginnings of the discussion. Actually, how do you know things? What can you measure from your back garden with the dark sky? And one of the things we asked an amateur astronomer to take pictures of the planet Neptune for us with a reasonable sized telescope, let's say about $10,000 or something. So a good but not ridiculous amateur telescope. And he took photographs of the planet Neptune on 4 nights over a month. I think it was the only 4 nights when it wasn't raining in Manchester. But you see it move. So it moves across the sky relative to the background, except it doesn't, of course, because Neptune's orbit is about 170 years or something like that, perhaps a bit longer. So Neptune itself is not moving very much. What's happening is that the Earth is moving around the sun. So what you're getting is what's called a parallax measurement. So it is exactly holding your thumb up in front of your eyes and winking like that, and you see your thumb moves against the distant background. And if you really want to, and you know the distance between your eyes, you can measure the length of your arm using parallax. Although it's a bit, a perverse way of doing it in a sense, but you can do it. And this is the same. So if you know the radius of the Earth's orbit, so you know how far the Earth has moved over a month, a 12th of its orbit essentially, then you can see how far Neptune moves and you can work out the distance to it. And this is how all distance measures in astronomy are calibrated. So they're all calibrated very directly using this method of parallax. If you go back through history, the great challenge, the Large Hadron Collider, if you like, of the 1600s, 1700s, those times, were the missions that went out to try and measure the absolute distance scale in the solar system. Because you don't have to rely on the Earth's orbital movement to get a big. Essentially, if you think of the Earth moving in six monthly intervals, you get a head the size of the diameter of the Earth's orbit, essentially. So you get a big parallax measurement. But in order to calibrate that, what you can do is measure the parallax shift in something from different places on the Earth, if you know the distance between them, which is an easier thing to know. And so throughout the sort of 17th century, very famous big expeditions went out to watch something called the transit of Venus, which was because it's when Venus crosses the face of the sun. And because you can measure the timings of that, you can see what's happening. It's quite complicated, actually, but it was worked out. I think it was Huygens or someone, one of the great astronomers, who worked out that by making those measurements from different places on the Earth's surface, you could get the absolute distance measure in the solar system. And from then on, you know everything, essentially. So you knew the distance to all the planets. You can weigh the planets by looking at their moons. You can weigh the sun. It all just cascades down. But then you can also do that for nearby stars. And indeed, that was done. So you get the distance to the nearest stars. You step out again, so you say, well, what's the distance to the nearby galaxies? Until the mid-1920s, we didn't know whether there were other galaxies. We didn't know whether things like the Andromeda galaxy, these misty patches on the sky, were just gas clouds or nebula in our own galaxy. It was Edwin Hubble who showed in 1923 that, in fact, the Andromeda galaxy is a galaxy beyond our own. We now know it's 2.5 million light years away. He did that ultimately not by parallax, because 2.5 million light years is way too far to see any shift. But there's a thing called the distance ladder in astronomy, which is very clever. So it relied initially on these early measurements of the Earth's radius. And then there was an American astronomer called Henrietta Leavitt noticed there's a particular kind of star called a Cepheid variable star, or Cepheid variable. The people pronounce it in different ways. But essentially, they're a star that have the property that they vary in brightness very regularly. And the period of variation of their brightness is related to their actual brightness. So once you can see these stars, and Leavitt calibrated it by looking at these stars in the Magellanic Cloud, which is a satellite galaxy of the Milky Way. So she knew they were all the same distance away, and she could see that they varied in brightness with different periods, and she could also see that they looked at different brightnesses. So she calibrated a measure. So once you know how bright something is, and you know how bright it looks, you know how far away it is. And what Hubble did was find one of these in the Andromeda galaxy. And he found it, so he knew how bright it should be, and he knew how bright it looked. And he immediately knew that the Andromeda galaxy was way beyond the Milky Way. And so you start measuring things like that. The final way you do it, there are many other ways of doing it, but they're all based on these things which are calibrated ultimately using parallax. The ultimate way you do it for the most distant objects is using something called redshift, which goes back to Einstein's theory again. So we live in an expanding universe. So that means that, let's say you look at something that's 1 billion light years away. Then what you find is that the light travels to us from the thing that's 1 billion light years away, and the universe is expanding. So that means the light gets stretched. And it gets stretched by the same amount that the universe has expanded in 1 billion years. So you say, well, how do you know that light is stretched? Well, you use the fingerprints of atoms. So, for example, hydrogen. Hydrogen gas always glows with a very particular signature, which we can measure in the laboratory on Earth. So it gives out light of very particular wavelengths. And you see, when you look at distant galaxies, that the further away the galaxy is, the more that light is stretched, which means it's shifted towards the red bit of the spectrum, longer wavelengths. It's called redshift. And you can calibrate that And ultimately, you can use that as a distance measure. So ultimately, you start using the so-called redshift, which is the expansion of the universe itself, to determine the distance to things that are, 10 billion, 12 billion light years away. Indeed, the most distant galaxies we see with the Hubble Space Telescope are over 13 billion light years away. And I should just say, one of the great projects that's been launched, the telescope to replace Hubble in space, it's called the James Webb Telescope. And its job is to look in the very red part of the spectrum, the infrared. It's more sensitive there than Hubble. And that means that you can see objects that are even more distant because the light has been stretched by a lot. The expansion of the universe over 13 billion years has stretched it into the infrared part of the spectrum. But the idea is that hopefully that we'll be able to see the origin of the first stars and the first galaxies. It's a big open question about what formed first in the universe. So after the Big Bang, the universe expands and cools. At some point, things start clustering together into galaxies and stars. What happened first? I think the best guess, or the theories, the best current theories is big stars form first, although it's quite controversial. So that's one of the things that we need to look at. But I think people lean now towards the idea of these huge stars, very short-lived, very bright, they collapse and burn and explode in supernova explosions. You get big black holes at their centers, and somehow that translates itself into the galaxies afterwards. So stars before galaxies. Is that true? That's one of the things the Webb telescope will hope to do by looking far away, which means looking right back into the distant past.
What I love about interviewing Brian is some people you interview and they have yes, no, or one-sentence answers. Whenever I have to interview him, I go 4 questions. That'll cover 2 hours. And I should say it is worth measuring your arm, first of all, however perverse it is, because then you'll know if you're doing it right. If your answer is 3 miles, the length of your arm, then you need to try again before you measure next.
You've got to make a precision measurement of the distance between your eyes, and that's why.
That's all you need.
And you do,
just to double check. Now, we will get. I want to talk a little bit about CERN, and then we are going to throw it open as well to the audience and anyone, by the way, who's watching outside. When we throw it open to questions, there's somewhere here, I'm not entirely sure where, there's a microphone set up that if you want to queue behind, and we'll take questions from you as well, so come into this room. I want to ask a little bit of kind of autobiography, though, which is, when did you, as a child, become so, well, basically in love with science? Because I think what you do, as people have just seen here, you enjoy expressing the ideas of science. This isn't just some kind of job. This is like Carl Sagan, a hero of both of ours, who was once asked, why do you want to express the ideas of science? And he said, well, when you're in love, you want to tell the whole world. And I wonder, when you, as a child, that point where, because you could have been a musician, as some people here will know, you were in a metal band called Dare, who supported Jimmy Page. You had a chart hit with a band called D-Ream, and then you made one video in the middle of the Lovell Telescope in Jodrell Bank, this is true, for the less successful single. And from that seemed to be the transition period where you went, well, I played the keyboards for a while. Now I think I'll just get down to understanding the universe.
It was. I get asked that a lot. The simple answer, the short answer I can give, is that I was always interested in astronomy, and I've thought, because I get asked a lot, I've thought about what it was, and I think it was something to do with noticing that you can tell the seasons change. Certainly, in the UK, it's a very obvious thing that happens, that you see that the Orion, in particular, the constellation, a beautiful constellation, rises, and it's a winter constellation. So it comes up as you're on the way towards the winter, when the school year starts again in September, and it tells you, it told me anyway, that Christmas is coming, or something like that. So the presents are coming. So I think it was something to do with making a link between the patterns in the sky that I saw from my garden and the passing of the year, which I've always rather liked. I mean, it's one of the pleasures of living in the far north, I think, in the northern hemisphere, that you get these very big seasonal shifts. And so I think it's something to do with that. But then, as you said, it was reinforced very heavily when I was 12 years old by Carl Sagan's Cosmos. And I think that one of the things we've talked about briefly tonight, and I think Sagan, for me, was the first person I saw do this, there's a very powerful element of polemic in Cosmos. It was made in 1979. The 13th episode, very famously, is about the threat of nuclear war, which was felt heavily, certainly in America at that time, and particularly by people like Sagan. And Sagan managed to make the connection between the perspective that cosmology gives us and astronomy gives us. Very famously, his brilliant writing later about the most distant image of Earth ever taken, the pale blue dot from the Voyager spacecraft, where he points out that when you see the Earth from a great distance, 4 billion miles, it's less than a pixel in Voyager's camera. And he wrote, many of you will have read it, but I recommend, if you look, pale blue dot, it's on the Wikipedia page if you type pale blue dot. Sagan wrote of he said, think of the rivers of blood that have been spilt over temporary ownership of a part of a pixel. And he translates this faint image into a statement about our responsibility to live together on this single point of light. And cosmos is infused with that. And it's the idea that by understanding nature better, you can learn to live in a better way on this planet, by seeing its physical insignificance, but its undoubted value. The fact that life is, certainly complex life is probably a rarity in the cosmos. What does that tell you? Imagine that in the Milky Way galaxy, we now know there are, by the way, recent measurements have told us that there are of order 20 billion Earth-like planets in the Milky Way. So perhaps 1 in 10 stars in the Milky Way has a rocky Earth-like planet around it. So it seems inevitable that there will be life all around there. But when you speak to biologists and you look at the history of life on Earth, you can make an argument that civilizations will be very rare. And Sagan would say, and I would say, imagine there's only one at the moment. Imagine this is the only civilization currently in the Milky Way galaxy. What does that tell us about our behavior? It should inform our politics. It should inform the way that we treat each other, the way that we behave as a global civilization. I hadn't seen that before. I hadn't seen that link made between knowledge, discovery, scientific exploration, and morality and politics, and Sagan made it. So when you've seen that at the age of 12, you think that's what I'd like to do. I'd like to find things out, but also always remember that the discovering these things about nature tells us, it can inform us, it can point us in the right direction about how we should behave.
It's kind of quite a poetic idea, isn't it? Quite a melancholy poetic idea that civilizations might be rising and falling across the Milky Way and across the universe, but never coinciding. So what happens is that each civilization sometimes makes it to another planet and either finds it just before life has reached that point of being detectable, or just after they've built the civilization decline. Again, another important to preserve and cherish the pale blue dot, in the words of Carl Sagan.
Yeah, I should say it sounds almost, Sagan was a wonderful deliverer of science, but he also, he had that kind of West Coast hippie-ness about him. And you could, sometimes you see people who don't think about what he was saying very carefully to accuse him of being a rather naive idealist, right? But actually, it's a very powerful point that Sagan made, and that all people who study the origin and evolution of life on Earth, or cosmology, every scientist gets a sense that there is undoubtedly something fragile and fortunate about our existence on this planet as a technological civilization. And I don't think that is a naive observation. I think it's a very powerful and deep observation. And it's one of the reasons that, I suppose, the responsibilities of people who talk about this science, one of the responsibilities we have is to make sure that doesn't sound naive. It's actually true. It's actually quite a real point. And there might be only one civilization in the Milky Way. That's a real point, a possibility. What does that say we should do? Well, I think it's fairly obvious that we shouldn't explode a load of bombs on it. That's a fairly obvious point, but it does put it in perspective.
I think we'll throw it out to the audience just to get some early questions, and I'm going to come back and talk a little bit about CERN and your work there and the work of other scientists. But have we got, if you'd like to put your hand up, and then I will point towards you. And so who would like to ask a question? I think you've covered all of physics. Well done. Oh, right at the back. Yes, sorry.
I'll move on
Was
to
that
biology.
at the back, or have we got any questions? Yes, right in the middle there. We'll take your question.
Yeah, my question's on the funding of science. I was at NASA a few years ago and quite amazed at kind of how small the NASA budget was. And, the points you were just making about the sort of pale blue dot. How do we get more finance and funding into science generally?
So it's a good question about because obviously all governments struggle, and it's obvious that there must be some optimal level, which isn't the whole of GDP. So somewhere between 0 and the GDP of a country, there's an optimal level. And of course, and I'm aware that a lot of research goes into this, that there is actually a kind of a general figure that's something around 3%, 4% of GDP, public and industrial investment in R&D seems to be some kind of sweet spot. I think there's quite a lot of work done on that. We're way below that in general. Some countries aren't, but most of the big ones are. Certainly the UK and America are below that now. It's interesting to note that the Apollo, I do know the number, so the maximum spend as percentage of federal expenditure, so not of GDP, but the government expenditure, was under 4% of federal expenditure. And I think it was 1966 that it peaked. And there was a big study done by Chase Econometrics on the amount of the payback of that investment, essentially by 1980, and it was of order 14 to 1. It was somewhere there's different studies. It's somewhere between 7 and 14 to 1 return. So every dollar invested in Apollo, let's say 10 came back into the US economy by 1980. Huge investment return. And you start to understand that for Apollo when you look at the fact that the age profile of the engineers, tens of thousands of engineers, I think the average age of the engineers in mission control when Armstrong and Aldrin landed on the moon was under 30. So, and Armstrong was the oldest guy in the room, actually, I think at 36 or something. So you see that what that big investment in that case in aerospace did was prime the US economy. So, and you can argue that the US industrial dominance in the last quarter of the 20th century is built to a large extent on those tens of thousands of young engineers that came through that program. So I think that when you look at investment in R&D, that the investment return in R&D, it's always huge and positive. And it's not only discoveries like, how do you quantify the graphene discovery at Manchester? You saw Andre Geim speak here a few months ago. That's potentially a multi-billion or even trillion-dollar industry. But actually, as big a spin-off, the knowledge and the techniques are those people, that educated workforce. So it's, so as I say, it's clear that we, as a world, we underinvest in R&D. The return is large, and if you ask where the cutoff is, from memory, I think it tends to, people think about, say, 3.5% of GDP in total tends to be, you tend to wash it out after that. So it's something like that, I think. The place to look to confirm what I said, because I'm not quite remembering the number, is the OECD website. That's a good place to look, but it's something like that.
I should say, by the way, if anyone does have it, don't be worried, because I know when you have a physicist on stage, sometimes you think, my question, it might be stupid. And I've been asking you stupid questions for 8 years now. But the thing to remind you of is, yes, he's very clever, but when we cross the road, I often have to continue holding his arm, because otherwise he forgets what he's doing halfway through, because he's thinking about the nature of the universe. So it's not all smarty pants, is it? So, have we got any other questions from... yes, just that person just there, I think, right in the middle there.
So if Einstein's theories have proven to be so accurate over such a long time, is there a reason why his theory of general relativity can't be reconciled with quantum mechanics? Does that say there's an error somewhere, or maybe something has been missed or something like that?
Yes. So Einstein's theory essentially predicts its own downfall. It says that, say, at the centre of a black hole, let's say, in a collapsing star, that there's no cutoff. It drives you in that sort of gravitational collapse to a point of infinite density, infinite space-time curvature. So it's a so-called singularity. But there are very good reasons to believe that that's not right. One of them is that we strongly expect black holes to be temporary structures. So they return their energy to the universe again, almost certainly, and this is through the process known as Hawking radiation, which is a first step, one of Stephen Hawking's great contributions. It's a first step towards bringing quantum mechanics and gravity together. And it has with an audience like this, it has the benefit of being quite easy to explain what's happening, actually. So I can do it if you want, which is that, so Hawking realized that quantum mechanics tells you that the empty space is never empty. So in particular, you can picture particles and antiparticles pop in and out of existence all the time. And so they pop into existence, they can borrow energy from the vacuum, if you like, for a certain amount of time before they return it to the vacuum again. And actually, the more energy they borrow, the less time they're allowed to borrow it for. That's called the energy-time uncertainty principle. So it's a fundamental part of quantum theory. So then you imagine on the so-called event horizon of a black hole, you get these particles popping in and out of existence. Just let me say, by the way, that these effects are measurable. And it's one of Feynman's contributions, one of the things he got his Nobel Prize for, showing how that in the light from hydrogen atoms, those little fluctuations have an effect, and you can take them into account. So we know they're there. So imagine on the event horizon of a black hole that the particles pop into existence, and they're going to come back together again. But one of them they end up on opposite sides of the event horizon. That means that they're what we call causally disconnected from each other. They can't come back. You've got one that's inside the black hole, if you like, can't get out. So what happens? Well, the particle that's outside is made real. It essentially radiates away, and it gets its energy from the black hole, ultimately. So the black hole radiates, it has a temperature, it shrinks, because it's radiating energy away, and ultimately it returns its energy back to the universe again. So you sort of know that there's no end of time there. There's nothing really wrong in the centre of a black hole. It's just that the theory doesn't work, and it must be that quantum effects and these things, that something must stop you having these infinities and infinitely curved space. And that's the challenge. So we know there's a better theory. The theory predicts its own downfall. Same at the Big Bang, by the way. But we don't know what the theory is. We've not been clever enough to put it together. But the first steps are being made with things like Hawking radiation.
So you think that a theory of everything, as it's sometimes called, is probably an inevitability at some point once we have the minds and the technology? Or
No, I don't know. It's one of those great struggles. People have struggled with string theory and ideas, trying to put these things together. But ultimately, the thing is, what you need is some experimental handle on these extreme conditions. So one of them might be gravitational waves, which might give you a window into extreme conditions where you might expect relativity to start making predictions that don't fit the data. And then you have a signpost. Another one, actually, just incidentally, at the Large Hadron Collider, so we're taking new data at the moment. In the old data, a few years ago, before we shut down for maintenance, there were hints that there might be new particles. Now, I'm not being political or trying to hide anything, but I don't know. But particle physics is a game of statistics, essentially. So it's like tossing a coin 100 times, and it is possible that you'll get 99 heads. Doesn't mean the coin is weighted. There's a possibility. And because we have 600 million collisions per second on average at LHC, or more, that means you've got huge numbers of collisions, huge amounts of data, so you're always getting things that look like new particles, and then they tend to go away again when you get more data. There's statistics fluctuating around. But we did have hints of which look very like new particles in the old data, and we need to take new data to see whether they go away or not. But one of them it's a famous thing. It's called the diphoton excess, and it was about 750 times the mass of the proton. Now, that's very heavy. The Higgs is 120 odd times the mass of the proton. So it's a very heavy new particle, it looked like, which was decaying into 2 particles of light. And so you can see that no one knew what this was, because there were over 200 theoretical papers published describing 200 different versions of what it might be. So nobody knows. Nobody knows even if it's there. It might go away. But if it stays, one of the suggestions is that it's this hint of extra spatial dimensions in the universe. So there are ideas which go back to the 1930s called Kaluza-Klein gravitons. And the idea is that you can have extra spatial dimensions that are kind of curled up small, so we can't see them. And the analogy that's often given, which is a good one, is imagine a hose pipe at the bottom of your garden, and if you're a long way away from it, it looks like a line, sort of a one-dimensional thing. But if you walk up to it, you can see that it's actually curved up into a second dimension, so it's a two-dimensional thing, a cylinder. So space can be like that. And one of the signatures is that you get these signatures of heavy particles, kind of towers of them, almost like harmonics on a guitar string. And this looks like one of those, if it's there. So if we're very lucky, we see hints of something like extra dimensions, then you start being able to probe these effects, so gravity potentially, try to understand gravity by looking at collisions in particle accelerators, and then you're on your way. So if that it's very exciting if it turns out to be true. I just don't know. Many of these things go away when you get more statistics, but occasionally you're taken by surprise.
Well, you get very excited. I think that it seems to me there's obviously many different kinds of physicists, but I remember when there was the possible result that neutrinos travelled faster than the speed of light, which I think was an Italian laboratory, and some people said, look, it's probably actually the equipment, there's something wrong with it, actually. But I remember Jim Al-Khalili, who's a British physicist, he was like, no, it's going to be rubbish. But you, when you saw that news, there was a glint in your eye that went, well, it probably is going to be a fault with the machine, but wouldn't it be brilliant? And you became, and that excitement of certain laws, certain ideas changing seems to be one of the things that constantly drives good scientific investigation.
I think it goes back to this idea we talked about at the start of we spoke about at the start of the talk about what science is. You're genuinely delighted to have your worldview demolished, and I think that's probably quite unusual, but very valuable. Imagine, I've always said, I don't know, it's kind of quite mischievously, actually, so I apologise. It's not meant to be offensive in any way to anybody, it's mischievous. But I once said that the Bible, which is, so that's the thing that I grew up in, that cultural thing, the Church of England, those things. So I just said that the Bible, if it said, of course we might be wrong, however, in the beginning, God created heaven and the earth, then it would be a better book. Not for any, no disrespect meant at all, but that idea that you could be shown to be wrong, just the recognition of it is a valuable thing, I think, and then to delight in being shown to be wrong, I think is the hallmark of a good scientist, but actually probably the hallmark of a good person, actually. I'd go so far as to say that. Can you imagine if we lived in a world where people were quite delighted when they were shown to be wrong?
Have we got any more questions? Yes, down there, question down there. Sorry, I'll tell you what, yes, if you can just pass the microphone down there. Thank you.
Thank you. Okay, I've got no science background, so I'm asking one of those dumb questions just to help me understand. So I'd like to know how you distinguish and identify the different kinds of things out in the cosmos that have an impact, because you were saying you're looking beyond light. It's not things that you can visually identify, but so much that you're talking about is theoretical, and so much is in flux. So, in your example of the big laser rulers in the States and the things that you can see are having an impact on the gravitational waves potentially, how do you distinguish what is having an impact and know that it's distinct from something different that might have an impact?
I think it's a good general question about science. I think one thing is that there are many independent measurements that build to our particular worldview at some time. So, for example, when you talk about the age of things, the age of the Earth, the accurate measurements come from, one thing is they come from radioactive dating, which is a very high precision technique to date rocks. And we can date the oldest rocks on the Earth, and we can date the oldest meteorites, and we can do those things. And we always get, for the oldest things, around 4 billion years or so, and you can hone it in from there. Then you can look at the sun, and you can say, well, we can do something called helioseismology, which is really like looking at solar earthquakes, if you like, solar quakes, and looking at the way the sun oscillates and rings. And you can use that to measure the amount of helium as a cross-section through the sun. So we know that the sun shines by making hydrogen into helium in its core, which would suggest that there should be more helium in its core. And we know how bright the sun is, we know how much energy comes out, so we know the rate of nuclear reactions that we need to produce that amount of energy. So we can look and see how much helium's there, and that tells us how old the sun is. And you get the answer, which is about 4.7 billion years or so. So from a completely different measurement, you get a measurement that's consistent with the age of the Earth. So you build up this picture, in this sense, cosmology, from many different measurements, and they all appear consistent. So then you judge, if you make a measurement that jars with that whole lot, then it gives you a sense of that makes you perhaps suspicious. But as Robin said earlier, you never dismiss data. You need to, if it contradicts the whole swathe of other experiments. Let's say we found out, well, actually, I'll give you a very good example, which is that in the 1990s, so in living memory for most people here, we had a measurement of the age of the universe, which at the time, based on the expansion rate we've measured, was about 11.5 billion years. And we had a measurement of the age of systems called globular clusters, which are old star clusters in the Milky Way galaxy. And the age of those was about 12 billion years. So the age of the universe was measured to be younger than the oldest objects in the universe. And that was the case in the 1990s. So what did people do? They just carried on measuring things. And then in 1998, a physicist who's now at ANU in Canberra in Australia, Brian Schmidt, and another team in America were looking at supernova explosions in the distant universe, and found out that they were dimmer than expected. And it turned out the interpretation was that the universe is accelerating in its expansion, a complete shock. It's like we thought the universe was slowing down. It turned it was speeding up. And that changed our measurement of the age to 13.8 billion years. But there was a time when there was a big inconsistency between the age of the universe and the oldest things in the universe, which were older than the universe. So you have to, you take data seriously, and you hold it, and you're allowed to have a contradictory position. You don't need to make a judgment. You say, well, there's something wrong, but we'll carry on measuring. And what you find almost always is that things, our worldview is quite sophisticated now, and the key thing is consistent. And this is where I mean, Robbie might want to comment. We on our radio show, we do have a little, because it's slightly comedy as well as science, we poke fun at the people who have strange ideas sometimes, and we kind of get a laugh out of it, so the people who, I don't know. Let's say you say that the Earth is flat. There's actually a movement now, a Flat Earth Society, and I get a lot of problems on Twitter with them. They say that I'm being paid vast sums of money by NASA to claim that the Earth is spherical, and I say, yes, I am. I get millions of dollars a year. It's wonderful. That's why I can stay at Raffles, and they get very annoyed. But the point is that, so you could say the Earth is flat, right? The problem is, though, that there's an interesting thing. They make a very interesting argument. They say they think that gravity that we feel is because the Earth is a flat Earth is accelerating through the universe. Now that's actually right. Right, as I said, Einstein's theory is that what we're feeling now, we're being pressed into our chairs because the ground is accelerating. The Earth isn't flat, though. Space and time are curved, and it's quite feat of imagination that you need to do some general relativity to work out how can it all be accelerating and yet the Earth stays spherical. And it's one of the things you have to understand general relativity. The thing is that bit's right. So they're right. It's called the equivalence principle. They're bang on. But the thing is that then to go from that to try and have a flat Earth causes problems with Newton's laws and with Einstein's theory and with all the things that we know about formation of structure in the universe. So the rest of it unravels. And that's what you tend to find from people who have strange ideas. They can convince themselves of one bit of it. And they may well be right. But the moment you start, the power of science is that you build a consistent view based on lots of independent measurements. So that's another long answer, right? But that's how you know. It tends to be consistency that allows you to be confident.
Well, that's I think one of the problems with some contemporary physics, if you don't immerse yourself in it, which is from a distance it can seem so counter-instinctual. A lot of what you're talking about in your book before you actually then get into the experiments is when you first see it, you think that doesn't seem right. And so you do end up with people being able to bamboozle you if they use an equation. They stick the equation up there, the equation's right. The fact that move 2, I think the one we talked about before, there's a person who does a lecture about homeopathy and the nature of the memory of water and why that works. And they put up E equals mc squared, and then at one point say, now, of course, how much mass are you? You're very little mass. In fact, if you took all the empty space out of the mass in the universe, all of that would fit in something the size of a basketball. So in a lot of ways, you can cross out the m of E equals mc squared. And in no ways can you. Because Einstein was very smart, he'd have made a shortcut if he could have done, if he could have made it E equals c squared. But you can see how people can be persuaded.
I'd say there's one, I'll just say very quickly, there's one that because we landed on Saturday, so we kind of a little bit jet lagged, and I was awake this morning about 5 o'clock, I think, and I woke up and I looked at Twitter, and it was the flat Earth people again, and one of them had sent me this thing, and I had to think about it for about 10 minutes because it was what they'd said was, so they'd got a diagram of the sun with the Earth going around it, and they said that so the Earth rotates once every 24 hours, and it goes around the sun. And so they were right. They'd shown that if that's true, the Earth rotates every 24 hours. This is where the problem is. But so then you can think about it going around, and it turns out that you get out of sync, right? So the day gets out of sync. So I sat there going, and it was a bit late at night, early in the morning. I was thinking, what's wrong with this? What's wrong with this? And I realised that. Eventually, it took me about 10 minutes. I sat in bed going, why is I didn't think they were right, but I thought, what's the explanation? The explanation is the Earth rotates once every 24 hours relative to what? It's relative to the sun. So the way we set our clocks is that it's 24 hours from the point the sun goes highest in the sky, and then you wait 24 hours and it's highest in the sky again. You wait 24 hours, it's highest in the sky again. If you measure that rotation relative to the stars and not taking into account the fact that the Earth's going around, it's 23 hours and 56 minutes. So it does get out of sync. And the stars rise at a different place every day. It's about 4 minutes, I think, later. Every day, the stars rise 4 minutes later, 4 minutes later, 4 minutes later. So they were almost right. It was very clever what this person had done. They got confused about something that really requires thought. It's like in their frame of reference, the day is not 24 hours long. It's 23 hours and 56 minutes long. And it does then the sun would get out of sync. It's called sidereal time. So it was very clever. So often these people are not idiots, right? But what they're doing is they're focusing on one thing, which is quite difficult often, and then being suspicious about the rest, and that's where they fall down. But this was quite a smart thing. So I tweeted them back and said it's the difference between solar and sidereal time. And they'll probably tweet at me now saying, you would say that, or something like that. But it was a good question.
I think we had another question in the same row. Yes, just at the end of the same row with the hand
Can
up.
we take one question from outside first?
Oh, yeah, sure. Yes. And then we'll
thank you so much for the fascinating sharing. Going back to what you said with Carl Sagan and sort of the responsibility for us to protect and preserve this planet, what are your thoughts on the viability of geoengineering? So large-scale human intervention to preserve the environment through carbon dioxide removal and solar radiation management. I ask this in light of the challenges sometimes of reaching an international an international agreement on environmental treaties and so on.
It's an interesting question that people suggest, and you can see in principle. For example, one of the engineering solutions I've seen for if the planet becomes warmer and warmer and warmer is that you can imagine putting mirrors or sunshades of some description up and reflecting sunlight away at something called one of the Lagrange points, which is the way where you can position things in between the Earth and the Sun, and so people talk about that. So I suppose that in principle you can imagine for just deflecting away 1 or 2% of the solar radiation back into space again by some large engineering projects, and you could do it. I suppose the great problem in terms of global warming is the rate, and the models are constantly changing and seem to be getting grimmer by the day. So I suppose that's the issue really. But you can see in principle, if you give us 200 years and some investment, you can see how you can imagine engineering projects like that. So there are things you could do. It's whether it's quick enough, I suppose.
We'll take the other question that was just on the... Yes.
Hello. This question is a tad more philosophical than scientific, but I was wondering, as a professor of science, would you argue that empiricism and deriving data through empirical observation is the only valid method of finding knowledge on a scientific basis? Or would you argue that there are other forms of ways to derive knowledge out there that we perhaps don't know of?
It's a good question, and I think about that a lot because I'm often accused of being simplistic, as most scientists are when they venture into philosophy, because you don't know the history of thought. In that, so, with that caveat, it does seem to me that the idea that you learn about nature by making observations of it is fundamental. And so whilst being aware of other arguments, I do sort of take a naive position on this. I mean, for example, if you look at modern cosmology now, so we haven't really talked about it, but one of the things that's interested me a lot recently is something called inflationary cosmology. And inflationary cosmology suggests that before the Big Bang, which means before the universe was hot and dense, the universe was doing something else. And we have very good evidence, I would say very good, from looking at the early universe and the structure, actually the distribution of galaxies in the universe today, that those theories that tell us the universe was doing something else before the Big Bang are at least possible, if not close to being valid and probably the standard model now, I would say. So standard textbook cosmology tells you there's this inflationary, it's called inflationary expansion. But interestingly, those theories almost all suggest, that so you've got this thing going on. It's the universe, just to give you the number, is in the most common version of the theory, the universe is doubling in size every 10 to the minus 37 seconds, which is a ridiculous, that's a millionth of a second. A 10 millionths of a second. Double like that. There's a number that I always remember, which is that means that if you had two particles that were 1 centimetre apart, then about 4 times 10 to the minus 36 seconds later, they would be 20 times the distance from the Earth to the Moon apart, right? So this is quite quick, this expansion. And it stops. And we have a valid model. It's called the inflaton field, and whatever it is. But this is an answer to your question. I'll get there in the end. But it stops, and in stopping, the energy that was driving that exponential expansion gets dumped into the universe. It hits it like an instant, like ringing a bell, and sets off sound waves in the universe. And we can see those sound waves. And quite remarkably, it's like throwing pebbles into a pond. So you get these spherical shells of density, essentially, going out from that initial impact of the end of inflation. And actually, you see galaxies, you see a predisposition for the galaxies today to be distributed on spherical shells like that, just a hint of it. So it's quite a remarkable theory. The point is, though, to answer your question, that theory also predicts that the universe doesn't all stop at once. In fact, it almost naturally predicts that the universe stops in a small patch and you get a big bang, and then the rest of it carries on and you get another small patch, you get another big bang, another small patch, you get another big bang, and it leads to this picture called the inflationary multiverse, where the suggestion is that there could be an infinite number of universes. And not only that, but the laws of nature can be different in every one, quite naturally. So you eliminate the need to worry about the fact this universe appears fine-tuned for life, which is one of the great philosophical and theological questions, that you say, well, even accepting the fact that we have to look out on a universe that allows us to exist, that's a trivial point, but still you're left with saying, well, if I just change the strength of gravity by a fraction of 1%, or change the amount of dark energy in the universe by a little bit, then we get a universe that doesn't allow life to exist. So why is it that we live in this beautiful universe? That's been a philosophical and theological interest right up to the present day. People debate. It's one of the ways of being a deist and talking about the fact that, could it be that a creator has fine-tuned the universe? If inflationary cosmology is right and the multiverse is right, you eliminate that argument. You say, no, that there are an infinite number of universes, every possibility exists, and this is inevitable. That, to me, seems to be a step that, in principle, observation, data, and theoretical understanding deliver something which is of profound philosophical and theological import. So to answer your question, that seems to me, I don't think you could have got to that if it turns out to be true. I mean, we're right at the beginnings of this kind of theory, but at the moment it fits the data. But if that's true, I do not see how you could have got there without making precision measurements of things like the distribution of galaxies. I don't think you could have got there by thinking about it. You would have had you could have just said, I think there are an infinite number of universes. People do, but it's contentless until you check. I think I don't think that's naive. Maybe you think it is, but I don't. So.
It's an interesting idea, because if you do want to find a non-empirical method of gaining knowledge, what method do you use, and then how do you test it? You may well have to use an empirical method to test your knowledge. Anyway, so there we go. That's
he's an English graduate.
The Goldilocks enigma is often what that used to be called, the idea of why it's fine-tuned. And it turns out if you have an infinite number of bowls of porridge, an infinite number of them will be just right. Yeah. An infinite number of them are terrible as well. So we had some more questions, and we're going to have to rattle through these. So
just a stupid question: why must light have a finite speed? Why not infinite?
Well, the very, very trivial question, the answer is that that's the way the universe is constructed. But there's a possibly a slightly better answer. I'll do it quickly, though, which is that in Einstein's theory, the finite speed of light is built into the geometry. It defines the geometry of space and time. So you can very briefly see that if you have a theory that says, based on experiment actually that led him to this, that says that space and time are essentially to be treated as dimensions. So you imagine this four-dimensional sweep of space and time. Now, obviously, we have freedom of movement in space. We can go anywhere, backwards and forwards and up and down, come back to the same place. But in time, we don't. We can't walk into the past. We can't halt our journey into the future, although we can vary the rate, actually, that we go into the future relative to other people. So there's something different about the time dimension to the space dimensions. And that difference in the geometry comes from a universal speed upon which everyone agrees. So it's a so-called invariant in the theory. And the last thing I'd say is that the speed of light is a red herring. If you know what that is, it's kind of it's a bad name for something, right? That light happens to go at the speed of light because photons are massless. And actually, in the theory, it is massless objects that have to go at that speed, and objects with mass that cannot exceed that speed. And the speed of massless objects is agreed upon by everybody, and that builds the geometry and stops you building time machines that allow you to go into the past, and leads to E equals mc squared, actually. My wife asked me once, why does E equals mc squared? I wrote a book on it saying this to answer her. Because you have energy equals mass. So you can kind of see energy, mass, yeah, we can change mass into energy and vice versa. The sun does it all the time, okay. But what's the c squared got to do with it? Why is the speed of light squared the exchange rate between energy and mass? And actually you can kind of start to see when you realise that what that number is something to do with massless things, actually. So it's a coincidence, as far as we know, that light travels at the speed of light. So... it's because it doesn't interact with the Higgs field, but that's a whole other thing that we can talk about.
So again, another question that someone said was stupid. It was not a stupid question at all.
It's a good question.
So, yes,
my book, Why
does
Does E equals MC Squared, is available from all good booksellers.
So just if you keep your hand up, just so they can see. Yep, there we are. And then we've got a question up
my
there.
question is, what do you feel about the supreme being and foreign intelligence? Meaning to say, life beyond whatever we know.
So I answer really truthfully that I think the only way that you can, which is I don't know. The one thing I could say with certainty in theoretical physics is we don't know where the laws of nature come from. Now, it is possible that the universe is eternal. With these inflationary cosmologies, there's a lot of debate about it, actually, because Stephen Hawking and Hartle had a theorem that said that any universe that always expands has a beginning in time. But there are people that that you can sort of get away. So that's cutting edge cosmology. I don't know what it would mean if it turned out that our measurements, going back to the previous question, suggested that the universe is actually eternal, and it's only our bit of it that had a beginning in this Big Bang 13.8 billion years ago, but there was something before that, we think. How long that existed for, we don't know. Did the framework exist forever? Is it logically necessary? Does it need to be laid down? That's cutting edge. So I honestly don't know. Is my answer. What was the second bit? Was life beyond Earth? So that's a question that we will perhaps answer very soon. I think there's a suspicion now that there may be life on Mars, microbes. It looks like the conditions necessary to support life are present on the planet. In particular, liquid water below the surface and some kind of geological activity. It looks very likely those conditions are also present on Saturn's moon Enceladus and Jupiter's moon Europa. So even on Pluto, actually, it looks like there's geological activity, a lot of water ice, which could be liquid below the surface. So, but the most likely missions are the European mission joint with Russia called ExoMars, which is part of it's already gone, an orbiting bit. There's a rover designed to go and look. And so there's within our lifetime, you can imagine a scenario where we find life has emerged spontaneously on another object in the solar system. Also, I should say, the other exciting thing is that we're at the level now where we can not only find planets around distant stars, we've found well over 2,000, but we can also analyse the atmospheres of the planets, and we're right on the edge of being able to do that. We've done it for some big gas giant planets, and we're looking, I think we've seen water vapour in one of the atmospheres, but it's a gas giant, so it'd be like Jupiter, so there won't be life there. But we're getting to the point now where we can start looking at the rocky planets. We're not quite there yet, and analysing the atmospheres, the chemical composition. And if, for example, you see a lot of oxygen, that's smoking gun for photosynthesis. Oxygen atmospheres are unstable. I don't think there's any geology known that can replenish an oxygen atmosphere to 20% like ours. It's photosynthesis. So you can even imagine the most speculative of all. People say, what if you saw something like CFCs in an atmosphere, which is an industrial fingerprint? But we're there now. Within the next 20 years, we're going to be there where we can start looking into the atmospheres of these rocky planets. So it could be we discover life on a planet beyond the solar system from its chemical signature. So
right, next question down there.
Thank you, Professor Cox. There are quite a few art lovers in this room because we're hosted by the National Gallery. And I'm delighted to learn tonight that you're actually a practicing musician. So my question is, well, actually, I'd like to invite your comments on the nexus between art and science, and how is art informing and influencing scientific thinking?
I think that put it this way, it's certainly true, and you know, the Apollo astronauts used to say this actually. But what is the meaning of our? We've touched on it before. What does it mean? What do our scientific discoveries actually mean? Those are questions that are perhaps not best answered by scientists, or at least a scientist is no better and probably worse at translating, trying to contextualize the things we find out about nature. The artists, novelists, philosophers, theologians, I think, likely better at beginning to answer questions or translate the things that we find out about the universe into I suppose, to understand what they should mean. What does it? If the thing that fascinates me, and I've referred to it earlier, is, and I should say that I'm speaking at a conference, a Church of England conference in September, and I was invited there because I have no opinion on theology. I don't know anything about it, but I know I can talk about inflationary cosmology. So I can say, what would it mean to us if it turned out there were an infinite number of universes, right? Which some religions think and others don't, and science had nothing to say until recently. Now it's possible that there are an infinite number of universes. What am I to make of that? I don't know. I suspect actually that you as an artist would have more to say and more understanding of how to think about that than I would. So I think that dialogue is absolutely essential if we're to contextualize the discoveries that we make rather than just make them.
I can recommend a book, by the way, called Stranger Than We Can Imagine, which is all about the artistic and cultural reaction to the discovery of the ideas of quantum mechanics. And it's a fantastic book, and also has a great description of wave-particle duality, which says it's like saying something's both a brick and a song.
I should say also that it's a two-way street. I mean, I should say that I'm well aware of the fact that it's obvious that the things we choose to study, that there's subjectivity in that, and it's certainly true. And scientists are often criticised. It was part of the question I think that was asked earlier, that you think that there's some absolute sort of logical mosaic covering of all the great questions, but actually, of course, the selection of the questions you choose to research, partly cultural, partly it depends on the ideas, the things that are interesting at the time. So I think there is a two-way feedback on what scientists choose to look at. You know, why did we start to choose to do astronomy? It's not entirely obvious that you have to do astronomy and look at the heavens, the points of light in the sky. You might have chosen to look at biology, and the idea that the fact that in Newton and Galileo and those people and Copernicus were interested in the heavens above is probably partly cultural at that time. They weren't trying to answer specific questions. They weren't trying to say, does the Earth go around the sun or the sun go around the Earth or whatever. They were just looking at the stars and the planets.
We had a question down there. Yes, question. And I think, have we nearly run out of time now? I'm not sure how much we...
I agree with you that good understanding of science makes better politicians. So I have to ask you, are you fearful of the advancement of science with Brexit? And a slightly cheeky follow-up question is, will you thus be migrating to France?
What was the second one? Was it?
Are you going to migrate to France?
I'm going to migrate to France. The answer, the honest answer I can give to that, and I think it's the correct thing to say, is that we don't know what Brexit is yet. And I think until someone has defined what it is, then the impact of it is not clear. Certainly, I think the main worry from UK universities is not necessarily we're very good at getting EU funding. I don't know if many people know this, but we because our university, I think there's something there that says 4 of the 10 greatest universities in the world are in Britain. That means we're good at attracting the funding. So we get £1 billion, euros, whatever. It's about £10 billion at the moment now, isn't it? It was $1 billion last week. But but the funding is not the point, and I think this applies way beyond Europe. Actually, the point is freedom of movement of people and freedom of movement of ideas and the ability to collaborate. It is so valuable, I think, in every sphere of human endeavour, in the arts as well as the sciences. But it's kind of it's exemplified in science, because science is so global. As is art, actually. I don't see any difference. The idea that you would move to restrict the ability to collaborate, I think, is the most serious thing. And that's why I say that until someone decides what it actually means, does it really mean restriction in the freedom of movement of people? If it doesn't, then it becomes less of a problem, I think.
And yeah, he's moved to
France.
I think we've nearly run out of time. In fact, we ran out of time about 25 minutes ago. But as you said, time may well be an illusion.
Sorry.
You've done some kind of equation on that.
It depends how fast you're moving.
Yeah.
Relative.
Thank you very much, everyone, for coming down, everyone who's hosted this. And the education is great. That's the great starting point, because education is great leads to the other 3 around here. Thank you very much.
Thank you. Sorry
Brian,
to overrun.
And hope to see you again.